Good afternoon and welcome to the 2023 Sentinel Innovation Day, which is sponsored by the Sentinel Innovation Center here at the Brigham Women's Hospital. My name is Sebastian Schneeweiss. I am the principal investigator of the Sentinel Innovation Center, closely supported by Dr. Rishi Desai, who will be taking over the agenda after a few intro remarks by myself and Dr. Robert Ball. The Innovation Center has quite an exciting, and here we want to mention the participating institutions in the core set, Duke University, Vanderbilt University, Kaiser Permanente, together with the Brigham Women's Hospital, who together make the core group of investigators and institutions, together with many other partners within the United States. The Innovation Center is in its year 4 and has been building and continues to grow a new data asset that is linking electronic health record data with claims data. And there are many obvious benefits. There are a bunch of more subtle benefits of such a linked data asset, which I sometimes describe the best of both worlds. Is compared to having only one or the other available for analyses. Now, with new data assets come new methodologic challenges. And for the first couple of years, Innovation Center, we have been working intensely on building tools, improving statistical methodologies to get the most out of this new and growing data asset. And today, you will hear 4 presentations, snapshots of several projects that are ongoing, among many other projects that are ongoing. And I'm really excited about the progress, and I'm looking forward for more great work to come. With that, I would like to hand over to Dr. Ball.
Thank you, Sebastian. And on behalf of FDA, it's my pleasure to welcome you to the Sentinel 2023 Innovation Day. And I'm very excited to see the progress that the Innovation Center has been making, really towards fulfilling the vision that FDA laid out in its 2019 strategic plan for the Sentinel system. A few years ago, we wrote a paper that was entitled A Roadmap for Integrating Electronic Health Record Data in a Causal Analysis Framework as really the focus of what the Innovation Center was doing. And with the presentations today, you can begin to see that work starting to come into focus. And you'll hear some very interesting talks today. As I think of them, they're kind of in 2 buckets. You'll hear about 2 frameworks derived from the work that the IC has done that provide generalized approaches to 2 key problems to fulfilling that vision. One is, how do you get better information from EHRs using advanced techniques like natural language processing and machine learning for computable phenotypes, and when is it appropriate to do that? And the other is an approach to integrating all this data and methods for causal studies that incorporates many of the important advances that have been made over the recent years. And then there's a deeper dive into 2, I think, very interesting projects solving important technical problems that will facilitate the further development of this infrastructure. So with that, I want to thank all the speakers, all the partners, and everyone who has been involved in this work for sharing it today, and welcome you all to an exciting meeting. And now I'll hand this over to Rishi to move on with the agenda. Thank you.
Great. Thank you, Bob, for those remarks, and welcome everyone. So my name is Rishi Desai. I'm an assistant professor here in the Division of Pharmacoepidemiology and Pharmacoeconomics at the Brigham and Women's Hospital and Harvard Medical School, and I will be moderating today's session. So we have an exciting lineup of speakers today, all representing the work that has been done through the Sentinel Innovation Center with support from the FDA. And the first speaker is Dr. David Carrell. He's an associate investigator at KP Washington, and his research interest lies in use of natural language processing to get meaningful information out of EHR data, and has years of experience doing that. So he will be talking about a general framework for developing computable phenotypes using EHRs. The second session will be led by Dr. Shu Shi. Dr. Shi is an assistant professor in the Department of Biostatistics at the University of Michigan. And her focus is on, for the talk today, is on harmonizing EHR and claims data across FDA Sentinel Initiative data partners, a case study and lessons learned. Then we will have a short break. After that, I will be introducing this process framework that we have developed called Principle. And then finally, Dr. Janick Weberpals, who is an instructor in medicine at the Division of Pharmacoepi and Pharmacoecon, also the Brigham and Women's Hospital, will be walking through his project, which was aimed to develop systematic approaches to handling partially observed confounder data from EHRs. And so, as Bob was already mentioning, this is really a blend of two types of work that we have focused on. One, presentations by David and myself are more big picture items where we are outlining some principles that these studies should really abide by to be generating more reliable evidence from these types of data sources. And presentation by Shu and Janick will be focused on specific problems, methodological challenges that we face when using EHRs, and how you would use these innovative data science approaches to overcome some of these limitations. And so I'm very happy to be moderating this session. A couple of reminders as we start. We will be taking questions and answers through the Q&A box on your Zoom screens. So feel free to post them as you have your questions. We will, at the end of each presentation for 3 to 5 minutes, we will focus on those questions that we receive. And then the presentations that are being delivered today will be made available on our website, sentinelinitiative.org, both the video recording as well as the slide decks. And so with that, I will hand it over to my colleague, Dr. David Carrell. David?
Thank you, Rishi. Great to be with you all today, and I'm excited to be able to present this work, a general framework for developing computable phenotype algorithms in Sentinel using electronic health record data. At the end of the presentation, there'll be a slide that acknowledges the large group of people that's contributed to this work. I just wanted to call that out in advance. This is not my work. This is the team's work that I've had a pleasure to be a part of. And also I wanted to mention that, Dr. Ball mentioned early on that there were these frameworks that were being presented today. This is one of them. And really this work is inspired by Dr. Ball's vision that to really move things forward, it's important for us to have some guidelines for how to do this, when to do this, when not to do it. When we started working toward this framework, we weren't quite sure where it was going to take us, but I think given the contributions of everyone involved, it was we got some really good benefits out of it, and I hope those can be clearly conveyed today. Next slide, please. Here's our outline, and I'll talk a little bit about the motivation for this work, and then I really present the general framework itself. There are these 5 steps. The last 4 are really the steps that we go through in creating computable phenotypes. We create gold standard data that we need for evaluation. Sometimes we use it for training data as well. We have to engineer features of the variables that are going to be used in models. We have to do the modeling and then evaluate the modeling. But importantly, and this came out of the work of the team that I was referring to, we recognize now that there's a first step, which is before you do any of the work, you need to think about whether the task to be addressed by a computable phenotype is really worth pursuing. And so we'll talk about that first. Next slide, please. Okay, and one more. Thanks. So, the motivation is really to improve Sentinel ability to conduct what are called ARIA analyses, these active risk identification and analysis system analyses that leverage packaged, ready-to-use analytic tools, plus the common data model from Sentinel to answer important safety questions. Next slide, please. An ARIA analysis is needed when a serious safety concern has been brought to the attention of the FDA. And ideally, that concern would be something that can be addressed through an observational study, which we call an ARIA analysis. However, the data available and the methods available in ARIA may or may not be sufficient to actually answer the question. If they are sufficient, then the ARIA analysis proceeds and we get the information we need. If they're not sufficient, then there's a couple of other things that can happen. One of them is quite expensive to actually conduct a post-market study, a whole prospective study. The other is another ARIA study. But what we'd like to be able to do is expand our tools and our data so that we could address more of these questions through ARIA analyses. Next slide, please. Okay, so when is ARIA sufficient? It's sufficient when the study population in question is available in the Sentinel data, when the things that need to be measured to answer the question can be measured, so the outcomes, say like anaphylaxis or an acute pancreatitis or whatever the outcome is, the exposures and any covariates that are important for controlling in those analyses. And then when the methods applied to those data can yield satisfactory performance and precision. In the recent past, ARIA has been insufficient for about 60% of the safety concerns. And so this is where the opportunity is for improving ARIA capabilities. The determination of the outcome itself. So did the patient have anaphylaxis? Did the patient actually have acute pancreatitis? Whatever it is often the reason for insufficiency. And it's because those things, even though there are diagnosis codes for those things, they're described in chart notes, it can be hard to, in an automated fashion, figure out when the patient really had it versus didn't have it. Here are some examples on the left of outcomes for which ARIA has been sufficient: GI bleeding, heart failure, lymphoma, and so forth. And some on the right where ARIA has been insufficient. Acute pancreatitis, anaphylaxis, I've mentioned, drug-induced liver injury, MACE when it results in a fatality, cancer, nerve injury, and suicidal ideation. A lot of the work that is going on in the Innovation Center right now is to enhance the data resources and the analytic tools to make more of these outcomes addressable through computable phenotypes. Next slide, please. So our focus is improving ARIA sufficiency. And here we are back to those key considerations that I mentioned in the introduction. First step will be assessing fitness for purpose. Should the phenotyping effort proceed? If the answer to that question is yes, then we need to consider 4 major aspects of phenotype development that I've already introduced. The challenge in all of this work is that traditional approaches to developing these computable phenotypes tends to be expensive and time-consuming. And because of that, it limits the number of safety questions that can be addressed with a given number of personnel, time, budget. What is needed in this general framework is a way to steer the development of those computable phenotypes in a more scalable direction. And here, by scalability, we mean not, computer scalability. Can you compute, millions of operations per second versus thousands or tens of millions, but rather how many phenotype models can you process, can you develop, can you bring to market, if you will, to address the question? And today I'll present this challenge in the context of 3 projects, one for modeling anaphylaxis, one for acute pancreatitis, and one for COVID-19 disease. Next slide, please. Okay, assessing fitness for purpose. Next slide. Assessing fitness for purpose is, as I said, the process for determining whether an effort to develop a phenotyping model should proceed. And it's useful, it's a critical first step because it can help us avoid spending our scarce resources on phenotyping efforts that are not going to be successful. To be successful, what we mean is an algorithm that can perform well enough to answer the safety question at hand. It's useful to think of this as a pre-mortem. We talk about post-mortems, what went wrong when something doesn't work right. But this is really trying to, in the abstract, imagine what could go wrong and assess that before we actually commit to doing it. That pre-mortem assessment is based on the combined judgment of experts with clinical expertise, informatics, chart review, EHR data expertise, and it considers all of those stages of development: gold standard data, feature engineering, model development, and model evaluation. One thing that we discovered in this work is that there's 2 important questions that can be applied to each of those stages of development that will help get at the question of whether or not a phenotype can be successfully developed. One is this question of the complexity of the clinical condition or outcome that's being measured. And secondly, is the complexity of the data that's going to be needed to operationalize that measure of the outcome. Next slide, please. So we found putting these clinical and data complexity concepts on a 2-dimensional space is useful. If you advance 1 click, we'll see the determinants of data complexity. Can you advance, please? Yeah, thank you. So the data can be heterogeneous. We'll hear from Shu Shi later today more about data heterogeneity. It can be obscure, imprecise. There can be irregularities. It can be unstable, such as the transition from ICD-9 to ICD-10. It can be high dimensional if it's NLP-derived data from notes, which can have very rich set of indicators. And it lacks structure sometimes, requiring things like NLP. Next slide, please. On clinical complexity, we have things like whether there's competing diagnoses, or we'd have to decide, oh, is it really acute pancreatitis or is it something else? There might be a lack of a definitive diagnostic test or a lack of consensus in the medical community about what the true criteria for that outcome are. And then also just limits in the clinical setting, and the time, knowledge, or technology available to clinicians. And so we can get in this 2-dimensional space, we can try to locate our phenotype, and this is part of the fitness for purpose exercise, to locate it in this space. For example, upper right-hand corner, we see anaphylaxis. And thinking about that and discussing that phenotype within a group of experts, we see that it has both high data complexity in terms of the information in the chart that needs to be processed to determine whether it's present, and also clinical complexity. It can be very difficult, even for clinicians reading a chart, a full chart, to come to the same agreement on whether or not the patient had anaphylaxis. On the other end, on the low end, diabetes, relatively easy to diagnose clinically. There are good tests for it, and the data are simple. And then other phenotypes could be in other parts of this space. So clinical and data complexity are very important. Next slide, please. Back down here where our arrow returns us to the slide. At the end of this process, we get a go or no go decision. If the recommendation is, no, the risk of failing on this phenotyping effort is so high, it's not good to proceed, at least as it's currently conceived. Now, that's not necessarily a dead end. It's possible to engage in a discussion about whether there might be alternative ways to formulate the outcome, or whether the same outcome could be targeted, but only say if the patient presented to an ED or an inpatient setting, eliminating the obscurity that might come with data in an outpatient setting. So it's the no-go decision may result in a conversation. If the decision is go, no harm done. We now have a better idea about what's going to be involved in phenotyping, and we can proceed. In terms of future work on this process of assessing fitness for purpose, one thing we've noted is that a difficult question is how much training data might be needed for model development. And yet that's something where some of the statisticians on the teams think there could be some more work that could help answer those questions. Next slide, please. Okay, on to gold standard data. Gold standard data is, there's nothing really revolutionary about creating gold standard data, except that it takes time and expertise, and therefore it's costly, and we can usually only do it for many fewer observations than we'd like to be able to do. We always need gold standard data for evaluation, and often we also use it for model training, though as you'll see, there are some alternatives to gold standard data for model training that are creating some exciting opportunities. The challenge in creating gold standard data, as I mentioned, is expensive, so we usually don't get as much as we'd like. Nevertheless, there are some best practices that can help us produce gold standard data in an efficient way. For example, the abstraction guidelines should try to follow as much as possible clinical diagnostic criteria. We also found that we don't have to have clinician or physicians review charts. We can have trained abstractors do that under the supervision of a clinician. Still have to do dual independent reviews to assess, make sure the quality of the determinations is maintained. And then, reuse tools, reuse forms, reuse approaches so that you're not recreating the wheel every time. In future work, there are some opportunities perhaps to further improve the efficiency of chart abstraction, for example, using some NLP-assisted interfaces that help reviewers more quickly identify content in the chart that might be relevant to the determination. Whether it's possible to also incorporate some silver standard surrogate outcomes that I mentioned into model training, reducing the burden on the need for gold standard data. And then sampling strategies that more efficiently target our gold standard efforts to patients or outcomes where the model will benefit from knowledge of whether or not those particular cases are the ones. Next slide, please. Here's an example of some projects listed in the left column there at different settings and with different types of gold standard data. And this illustrates the problem. If you could advance the slide once, we'll see that traditional gold standard data in these three projects, anaphylaxis twice and acute pancreatitis once, can generally, we can afford to have 200 to 300 gold standard cases. But what really impacts the ability to develop models with that data is how many cases or how many observations are in the smallest of the two sets. So here we see for anaphylaxis, the smaller group was always the non-cases, 85, 97, and 118. The model doesn't care whether it tries to solve the problem by identifying cases or identifying the non-cases. So those non-case numbers become the rate limiting factors in terms of how many variables and how complex a model can be to try to identify that outcome. If we advance again, we'll see here that silver standard labels can allow us in these phenotype here for COVID-19. We had thousands of observations with silver standard labels. We still needed gold standard data to evaluate the models that were developed on silver standard labels, but it gives us much more training data. Next slide, please. Okay, on to feature engineering. Now, feature engineering, the goal here is to measure the things that are going to help a model distinguish true cases from non-cases. And as I've mentioned, the challenge is that manual approaches to doing this, and honestly, the approach that I've spent most of my life using is very time consuming. It requires expertise. No two informaticists or clinicians are going to actually do it the same way independently. So there's some operator dependence. And because of that, we really don't know if all of this effort that our experts are devoting to engineering these features makes a difference in the outcome of the model's performance. And so it's possible that some of this effort is wasted. If we take a look at the next slide, we'll see overall we can organize engineering into these three groups. On the left is identifying the phenotypes. This takes discussions with experts, review of knowledge, looking at code sets. If there's NLP, it takes looking at notes, proposing terms and concepts that need to be extracted. All of that takes time and expertise. In the middle, if we advance one more slide, we'll see that defining those targets or those features to be engineered also is a time-consuming and expert-heavy activity. Code sets have to be validated, reviewed, make sure there aren't things in there that we didn't want to include. If there's NLP involved, we need to really test and validate the NLP system to make sure that it's building that feature exactly in the way that we want, and then specifying the logic. And then finally on the right, it's the code to implement the features or create the NLP system has to be written, developed, QC'd, and ultimately put into a data set. So it's a very time-consuming, very expert-intensive process. If we advance one more slide, we'll see that it's just a lot of people, a lot of expertise involved. Next slide, please. Alternatively, there are automated approaches that we've been experimenting with to do this same type of feature engineering that gets us away from a heavy reliance on people and manual effort. These three papers, all in AMIA from a group out of Harvard led by you and colleagues, describe this work. If we could advance the slide, we'll see that there's some general principles here. The first principle of this work is that, despite our love for structured data and its availability in our common data model, we should instead focus on clinical text as the primary data source for modeling. Secondly, instead of relying on discussions between clinical and informatics experts to engineer features, we should use data-driven ways to extract what features might be needed from published articles, from public knowledge sources, and then use data-driven engineering methods. Next slide, please. So in contrast to the manual approach, if we click once more, we'll see here, the first step in an automated approach is to identify the features. And this, we find, based on the work cited in the previous slide, can be done by identifying here's a set of 5 knowledge-based articles describing what anaphylaxis is and how it's diagnosed and treated, one from Mayo, there's some from Medline and so forth. We can process those articles with our NLP system and a standard dictionary. We can find all the medical concepts that are mentioned in those articles. And then we can use a simple rule that says if a concept appeared in at least 3 articles, then let's keep it in our list of potential features. And so we might get between 100 and 300 different features. Next slide, please. Optionally, we could have this list reviewed by a clinician, but it turns out this isn't really necessary. And even if you did want to use it, it doesn't take a lot of time. Next slide. Then we implement the features. And if you click once more, we'll see a line here. We're going to take those 100 to 300 concepts we got out of the knowledge base articles, and we're simply going to find how many times each of those appears in a patient's chart notes. The purple diamond there shows we'll just count them. We'll simply count them. And our data set then will have a column in it for every patient, and we'll say how many times that particular feature appeared. So we now have, say, 100 to 200 or 300 features per patient. So click once more, we'll see, this is a much lighter burden, much faster compared to a manual approach. One more slide. And one more, please. So really the advantages come down to automated approaches have shorter development time, little or no need for domain expertise or informatics expertise, reduced operator dependence, making it highly replicable. The question remains, is it going to work? And that's something we need to find out. Next slide, please. Here's an example of structured data features that were manually engineered for an acute pancreatitis model. If we click again, we see an example here. Lipase labs within a time window around a patient's admission to a hospital or an ED setting. It turns out that's a very powerful feature, but we also, the clinicians told us, well, we need to engineer features for competing diagnoses. So the majority of these other features are ways to try to see if the patient has a history of other conditions that might also explain what we're seeing for symptoms that isn't actually acute pancreatitis, but something else. Next slide, please. Likewise, engineering NLP features can be time consuming. This is a summary of 843 different terms that were engineered for an anaphylaxis feature set. They're organized by colors here, which correspond to the symptom categories that are used to diagnose anaphylaxis. And you can see from the numbers in parentheses after each one, sometimes there are many, many different ways that some of these concepts can be mentioned in text, which makes it more complicated, more difficult to manually engineer them. Next slide, please. In contrast, this is a set of features that was generated by that automated approach, harvesting these features from knowledge base articles, in this case about symptomatic COVID-19 disease. It turned out there were 158 features that appeared in 3 of 5 articles. And so for each of these, we simply count the number of times they occurred in a patient's chart notes. Advanced again, you could do things like have a clinician say, oh, which of these were related to severe disease? And maybe you could use that information, but again, that's optional and not a heavy burden. Next slide, please. So best practices for feature engineering, always rely on domain knowledge, but consider whether you might be able to get a lot of that knowledge from published sources. Should always engineer as many features as you feel might be useful, particularly if it doesn't cost much to do so. The modeling step can deal with that, as we'll see in a future slide here. And then really, to be efficient, you need to carefully consider when manual curation should be used, and should use it sparingly for targets that you believe are really going to help distinguish cases from non-cases. You need to think about generalizability, because many of these models will be applied across multiple settings. And if tailoring is needed, you should build that tailoring into the modeling process itself. Future work is, as I suggested, is seeing how some of these automated approaches could be used, maybe at least as a starting point, and sometimes maybe as a solution. Next slide. Okay, on to model development. Advance one more slide. So the goal in modeling is to develop useful prediction models. The challenge is that sometimes the relationships between all of the signals that might be in a patient's charts or data and the outcome are very complex. And so a model might need a lot of training data, and if to accurately represent those relationships. And yet, if we rely on gold standard data, as we saw in some of those examples, it limits the number of observations we can train on. So our best practices are always incorporate the domain knowledge when you're approaching the modeling question, but also do things like use outcome blind dimension reduction to say reduce from a set of 150 or 300 features down to those that are going to be more useful for model identifying cases and non-cases. And then also consider diverse sets and combinations of modeling strategies. We'll see that in the next slide. So by dimension reduction, we, in the box on the left, we could use a PAM or partitioning around metoids, so clustering our variables and then only choosing one per cluster. That's one way to reduce them. We could also use lasso regression to figure out which features have very low or zero coefficients in a regression model and leave those ones out. Or we could just retain all the features. There's nothing wrong with doing that either. In the middle, we have here 8 different algorithms, from simple, more linear regression things to very complex machine learned models. And you can combine each of those to create 24 different combinations of feature engine reduction and modeling steps. And then you can add a 25th one, which should just be do all 24 and then combine the results. Next slide, please. So back here at the arrow on the left, another recommendation is to use V-fold cross-validation is the most efficient way. So instead of saying dividing our training data into like a 60% training set and reserving 40% for validation, we can divide it into many, many small sets, train on, say, 20 small sets, train on 19, evaluate on the set that's held out, and just go through around the circle until all 20 sets have been included in a validation. Future work here, again, is how to incorporate some of the time-saving silver standard surrogate outcome labels into the modeling process. Next slide, please. Okay, evaluation and reporting. The last step in the engineering process. And this, the goal, of course, of evaluation is to understand if the model is going to perform well enough to address the ARIA question when it's applied to data that it's never seen before. A challenge of evaluation is there is no alternative to gold standard data, so we have to have it. Another challenge is that, and this is coming from our statisticians, is that bias and variance of causal effect estimates can depend on the sensitivity and the PPV of a model. So you have to really think about the question being asked and what performance characteristics you should feature or you should focus on when you're doing your evaluation. Best practices are to consider lots of performance metrics, use cross-validated metrics, and for FDA safety outcomes, choose cut points of predicted probability to find cases and non-cases, and see how that impacts performance. If we go to the next slide, we'll see an illustration here from data for an acute pancreatitis model. Where the vertical line is if we choose that as the cut point in predicted probability, we see we get really nice model performance characteristics where PPV and sensitivity are both above 90%. We're not always this lucky. In the next slide, we can see here's anaphylaxis. As I mentioned, a more clinically complex and a more data complex phenotype. PPV and sensitivity cross somewhere below 80% in the development site, and then when we applied it to data that had not been used to develop the model, we saw a 7% drop. So progress, but still, we expect to see this kind of loss in performance when we go to unseen data. Next slide, please. Then just a reminder on narrowly focusing on high PPV could undermine the power to detect non-null associations. So it's important to pay close attention to the statistical advice during the evaluation process. And then always, evaluation should depend on what the downstream use case is, and also consider the transportability and the generalizability of the models. The next slide will show us what we mean by this. On the left here in the gray box, if we considered all of the, say 24, 25 models combined that we considered, which one of these should be used for to answer the safety question? And there's really three sets of questions that need to be addressed to choose one of them. First of all, does the model perform well? That's the obvious one. And that will eliminate some of the models. You can see in here yellow, the ones that are retained. Among those that perform well, which ones are going to be easily transported to other sites? Is the data available? How difficult is it to implement the covariates and the modeling? How interpretable and simple is the model? That might reduce others. And then finally, in the right-hand side, the blue box, is it generalizable to other settings, other institutions, time periods, or patient cohorts? May not yield a single model, but then you can make an intelligent guess and or choice and come up with a single model. Next slide, please. So, and advance once more. The future work here is really to investigate how biased in these effect estimations can be reduced by possibly by defining the outcome instead of as a binary case non-case outcome as the predicted probability of being a case. So using all of that information, there might be some benefits there. And then also we're thinking there could also be some instances where some models with certain characteristics could be used in other settings without requiring that they be reevaluated with new gold standard data. But those are statistical questions that require careful analysis. Next slide, please. So implications and next steps briefly. We know that NLP and machine learning can help, but it's important to, in this general framework, to think about, should you proceed? What's efficient? How can tools be reused? And always, how's generalizability going to be maintained in these phenotyping efforts? Areas where future work can be done, NLP-assisted chart review to reduce the time needed for chart reviews, and strategic sampling to reduce chart review effort, automated feature engineering approaches, which also may involve using silver labels instead of just gold standard labels, probabilistic case definitions instead of the binary ones, and then when we can reuse our models. Next slide, please. Again, I wanted to call out an incredible team from many different institutions here that have contributed to this work. And I'll leave it at that, and we can move on to the next slide and see if there's any questions. Rishi, I'll turn it over to you.
Thank you, David. That was an excellent presentation. So this floor is now open for questions. I see we have received one question by an anonymous attendee. We can start there, and then as people are thinking, maybe more questions will pop up. So David, this is a question regarding the data adaptive methods. So someone is wondering if it's worth mentioning if these cross-validated model building activities that you suggested are being used to estimate the causal effects. It's important to use a doubly robust estimator like a TMLE or augmented inverse probability weighting. Otherwise, the estimate would be expected to be biased and the variance would not be estimated correctly. So do you have any response to this?
Yeah, so first I'll say, this is definitely a question that our team could answer, but I am not the statistician. And so I'm not going to be able to respond. This sounds like a very thoughtful comment and one that needs careful attention. So that's really all I can say.
Thank you, David. Yes, so I think that there is just a lot to be learned here. So we are I think taking baby steps in terms of how we are approaching these data adaptive methods for outcome definitions. I think this is very new for Sentinel and very new for the field in general, I would say. So excellent question. Thank you. But I think there's just no definitive answer at this point for this one. So there is another question from Ryan Hickson, who is wondering if the relationship between ideal cutoff for sensitivity, specificity, and PPV and causal effect or bias variance is dependent on whether we are talking about the exposure, outcome, or confounder.
Yeah, it's another good question. And one thing about our phenotyping work that we've done with this group that led to the development of this general framework is we did not consider exposures. We were really trying to say, can we accurately identify the outcome? So now when you have an exposure group to which you will limit your analysis, definitely there could be some other considerations there.
Yeah, it's just so much to learn. Again, same comment, David. We are already thinking about some of these concepts in our other work as well, with the confounding and what are the different motivations there and things like that. So great question by Rand there. Next question from Marian saying, could you elaborate on the engineering feature generalizability across settings under best practices? Across settings, how do you kind of
So one thing, like with these automated approaches to feature engineering, they're so simple to implement. There's no reason not to implement them in each setting. I mean, ultimately, in fact, you have to implement the features in order, even if the model is trained in one setting, to apply it to another setting, you're gonna have to implement the features. Well, once the features have been implemented, these automated approaches to modeling are so simple. And, I don't want to simplify the work that Brian Williamson and others have done to make that model development easy, but it is pretty much a cookbook approach running some very sophisticated code. And so you can retrain the models in each setting. And then also independent of that, because you're not manually tinkering with the definitions, you're just taking a standard electronic medical dictionary and counting the occurrences of those across settings. There's a lot of uniformity in that. Still, maybe some settings are going to be more verbose than others, but that's where the ability to retrain the model within each setting can overcome some of those challenges as well.
Great. Thank you, David. So I think that we have received some really interesting questions. So thank you to all the attendees who posted the questions. In the interest of time, I think we should probably keep moving and hand it over to Shu, who will be talking about her work with Sentinel. Shu?
Yes, thank you,
Take it
Rishi.
away.
Yeah, thank you. Hello, everyone. Today I'm going to talk about a particular case study where we focus on harmonizing EHR and claims data across FDA Sentinel data partners. Next slide, please. I'll start with a background and motivation, and then we'll talk about overview of methods that we applied. One key thing to notice is that there are two big components of the project. The first component is how do we compare coding patterns between two sites to answer the question of are medical codes used differently between two sites? And then the next component is if we do detect coding differences between sites, can we sort of mitigate it? Can we create a code mapping between them and use that mapping to harmonize EHR data? So code comparison and code mapping are the two main themes of this project. And then we'll talk about results, how we validate those results, and end with a conclusion. Next slide, please. And next one, please. Yeah, so probably everyone knows about Sentinel. So over time, the FDA Sentinel has created a distributed data network through partnership with many healthcare institutions. And we collect claims and EHR data routinely from 17 data partners with over 1.09 billion person-years of diagnosis and treatment information. That means there's a ton of information about patients that allows the FDA to monitor drug safety and also generate real-world evidence. Next slide. Now, within such a distributed data network, Sentinel has created an infrastructure to protect patient privacy. Basically, the individual level data always sits behind the firewall, and an analytical center will send generic codes to each site to generate summary information and aggregate them at the center. To make this process possible and automated, we need a common data model. So Sentinel has created a Sentinel common data model such that each data partner use the exact same type of standardized medical codes and have a list of the same data fields and same type of variables, such that you can always send generic codes to each site and operate them. Next slide, please. So this sounds very nice. However, a big challenge with the Sentinel common data model is that although the common data model unifies the vocabulary, right? We're always using the same set of medical codes. It doesn't unify the dialect of medical coding within each heterogeneous data partner. Here's a toy example where we have two healthcare systems, system A and B. And as you can see, they have been restructured into under the Sentinel common data model. Now, suppose we built a phenotyping algorithm for anaphylaxis using data from system A. And one key predictor is shortness of breath, which for ICD-9 code is 786.09. And then let's say we apply this algorithm to system B. However, it turns out that at system B, they exclusively use a different ICD code, which is 786.09, that describes dyspnea, which literally means shortness of breath. Then you can imagine that the performance will be dramatically dropped, but it's not a problem of the method, but rather a problem of how data, how information are captured. So that motivated our project. Next slide, please. We call it the Sentinel Data Harmonization Project. And there are, so DATA stands for 4 steps. First, we would like to describe, are there any differences in medical coding between two healthcare systems? And then we would like to align codes between the sites. And then we would like to use the aligned data and codes to better transport either a phenotyping algorithm or a statistical model trained at one site to identify outcomes at another site. And ultimately, we would like to apply it to across all data partners. And we're going to go through a case study with 2 Sentinel data partners, which are Kaiser Permanente Washington and Kaiser Permanente Northwest. Next slide, please. Next one. So we're going to talk about the methods for code comparison and code mapping. The first goal is to compare coding. And the idea here is that for each individual code, we have how frequent they're used for each patient between the 2 sites. So naturally, we can do a 2-sample t-test, right? Compare how codes are used between those sites. Now, alternatively, because codes are naturally collapsible into groups, so we can also do group level comparison. And the idea here is to think of medical codes within a group as genetic variants within a region, so that we can apply group-wise association tests in genetic research, which are SCAT, sequence kernel association test, and the burden test. So basically, for comparing coding patterns, we will do code level comparison and group level comparison, really to look into whether there's any differences in coding between KP Washington and KP Northwest. Next slide, please. A key challenge is we don't get access to individual level data. So our team has created a new privacy preserving test for both code level and group level comparison. Basically, those tests only require summary level data. Next slide, please. And here's a validation of the method. It's a 3 blocks of very boring plot where all the dots are lined up on the diagonal, which basically means if you calculate p-value based on summary data and compare that to p-value based on individual level data, you get exactly the same results. So that validates that our new privacy preserving methods are actually working. Next slide, please. Okay, so first goal is code comparison. Now let's come to the second goal, which is code mapping. Suppose we do detect a lot of coding differences. Can we create a mapping between 2 sets, between codes from 2 different data partners? And here's an example, and I'm not sure if people can see the gray line between the, the 2 sets of ICD-9 codes. On my screen, they're disappeared, but hopefully I'll explain what I wanted you to see. So on the left, we have ICD-9 from Partners Healthcare. On the right, we have the same set of ICD-9 codes from VA. So recall that the challenge is because of data heterogeneity, the same ICD codes might mean different things at different sites. And in addition, different codes can be used exchangeably because they're synonyms. So what we found out is that actually 786.09 on the left have been mapped to 0.05 on the right. And they both talk about shortness of breath. So our final goal is to reach at such a mapping that allows us to better grab information when we transport an algorithm from one side to another. So how do we get to this? How do we get to this mapping result? Next slide, please. This is our overall method for code mapping. There are 4 main steps. The first one is data preparation. We want to filter out rare codes that doesn't bring in lots of information. And the next step is something called code embedding. The idea here is to represent the meaning of codes based on latent features, such that each code is represented by something called the embedding vector. It's a numeric vector, and the direction of this vector tells you the meaning of the codes. And 2 codes with similar meanings will have very similar directions. And then the main 2 steps are steps 2 and 3, the last 2 steps, which are called space alignment and code mapping. So the idea here are we will generate 2 sets of code embedding, one from KP Washington and another from KP Northwest. So each of them creates a language space. To be able to talk about distance in the same space, we need to first align the 2 different language spaces. So that's space alignment. And then once we align them, then we're going to create code mapping by doing the following. For a source code at KP Washington, we're going to find the nearest neighbor among the target codes from KP Northwest. And of course, we're going to talk about how we define nearest through some distance measure. Next slide, please. Okay, so a little bit detail about how we generate code embedding. Next slide. The way we generate code embedding is by looking at which codes co-occur with each other. This is because if 2 codes have similar meanings, they should show up in similar contexts, which means they will have similar neighbors. So what we do is for each patient timeline, we chop it into time windows, and then within each time window, we calculate for each pair of codes, how many times do they co-occur. And we sum up those counts across all patients within each Kiter site. That gives us something called a co-occurrence matrix. And then what we do is a procedure called singular value decomposition, which basically reduces this big matrix into latent features. So those latent features talks about the meaning of the codes and relationship among codes. Throughout this process, there are 2 tuning parameters. One is how long is the time window that I count co-occurrence, and the other is what's the dimension of this embedding vector representing codes. And I'll talk about how we tune those parameters later. One thing I do want to mention that will be very important for later steps of the method is how do we measure distance. So if you look at the figure on the bottom left, these are 2-dimensional code embeddings for ICD-9 codes 250, 405.99, and so on. And as you can see, because 250 and 0.405 have similar relationship, like they're highly correlated, so their angle are pretty small. As a consequence, if you calculate the cosine of the 2 vectors, it's very high. So we define this measure as cosine similarity. So cosine similarities are a number that ranges between -1 to 1. Higher cosine means code embedding vectors are closer to each other in the embedding space, which means the 2 corresponding codes are more related. So this is one way that we're going to use to measure distances between different medical codes. Next slide, please. All right, so now we're going to talk about how we do code mapping. Our input data are the 2 sets of code embeddings trained from KP Washington and KP Northwest. And there are 2 steps for code embedding, space alignment and code mapping. Next slide. There are 3 methods that we're going to implement, and they differ by how you align the language spaces and how you do mapping. For space alignment, if you focus on the 3rd row, there are 2 main methods. We call them projection-based alignment, PA, and rotation-based alignment, RA. For projection-based alignment, basically you do a linear regression, which basically projects the different embedding vectors from one site to another. And throughout this process, you can imagine a linear regression will stretch the vectors either longer or shorter in the projection process. And alternatively, we can do rotation-based alignment. And the key difference is that you don't stretch them, but rather you keep the length of the embedding vector and you only rotate one set of embedding vectors to align with the other set of embedding vectors. And that's implemented by something called a spherical regression. So once you have done space alignment, the next step is to actually find code mappings. For each source code, we want to find its nearest neighbor among the target codes. And there are two ways to measure distance. The first one is directional similarity, which is the cosine similarity that we just introduced. The other one is regression similarity, which is the association or the coefficient of codes when you run a regression. One way to distinguish those methods is that directional similarities are unadjusted association between a pair of codes, whereas regression similarities are adjusted association between a pair of codes, and we call them DS and RS. So if you pick different combinations of step 2 and 3, you'll get different methods. Our main method is RADS in the middle. So basically that means for space alignment, we use rotation-based space alignment, and for distance measure, we use directional similarity. We also implemented two sensitivity analysis, which are PADS and RARS that I'll talk about later. Next slide, please. Okay, so here is just a little more detail about the two different distance measure. How do we do code mapping? How do we find nearest neighbor? And I'll skip the detail, but just summarize them that there is adjusted versus unadjusted association. Here is a summary of our main method, RADS, rotation-based alignment in step 2, where you do a spherical regression, and then directional similarity in step 3, where you find the largest cosine similarity. Next slide, please. Okay, so far, when we create code mapping, we have been focusing on information coming from code pair correlations, so pairwise relationship between each pair of codes. One additional information that you can leverage is the individual code distribution. So how frequent are each code? And the rationale is if I have a really good mapping, then it should match code frequency from one side to code frequency in the other side. And based on this knowledge, we develop methods that can further improve the mapping matrix based on pairwise relationship. And we're going to implement it as part of the main method. Next slide, please. Okay, so now I'm going to spend a little more time on the results. First, finally, we can talk about our study population. Our study population is continuously enrolled KP Washington and KP Northwest members who are 50 and older with any diabetes. This takes up 10 to 15% of the Kaiser Permanente patient population. The reason we choose this study population is that, first of all, for patients with diabetes, they have more frequent encounter, and that gives us longer period of observation. So that means better power to generate things like code embedding. Another very important reason is because when we look at coding comparison, right? There are two sources that leads to a difference. One is how different are the patient populations between the two Kaiser sites. And the other is, on top of that, whether there's any coding practice differences. We want to distinguish those two. And one way to do that is to strictly define a study population between the two sites that's the same between the two sites, such that we can roughly believe that there's no patient population level differences. So any differences we detect can be attributed to coding practice differences. The study period is between 2011 and 2020. This is 10 years spanning the ICD-9 and ICD-10 era. So for such a study population, we have a total of 65,000 unique codes that includes both ICD-9, ICD-10, and as well as CPT codes. The table in the bottom shows the number of patients, total code counts, and breakdown by different type of codes, comparing KP Washington and KP Northwest. Basically, we have roughly similar frequency of code usage, and there are about 87 number of patients and 1,000 of patients at KP Washington and 71,000 at KP Northwest. Thank you. Next slide, please. Here's a table 1 that compares patient characteristics between the two Kaiser sites. Roughly, they're very, very similar. The only thing we wanted to draw your attention to is the right panel hemoglobin A1C, you'll see that there's a larger percentage of missingness, 40% at KP Washington and 4% at KP Northwest. We digged into the reason for that, and we found out that you don't get to observe HbA1c value if it's paneled at a contracted clinic. And it turns out KP Washington have quite a lot of contracted clinics, and that's why we have a larger percentage of missingness at KP Washington. Next slide, please. Okay. So back to the two components of the project, we want to first do code comparison and then try to reduce the coding differences by conducting code mapping. For code comparison, we want to do both group level comparison and code level comparison. Here's the result of group level comparison based on sequence kernel association test. If you look at the figure, the x-axis is frequency ratio. So comparing the frequency of each group of codes between KP Washington and KP Northwest. More extremely left are more usage at KP Northwest, and on the right are more usage are in KP Washington. The y-axis is the p-value, and higher means more significant. Each code type each color correspond to a different code group, and they're color coded by the type ICD-9, ICD-10, and CPT. So we found that there are actually quite a large percent of codes that have significant differences, 33%, which is 800 out of 2,500 code groups. And not only the significance, but also the magnitude can be very different. There's about 4% with a frequency ratio that's larger than 5, which means KP Washington tends to use certain group of codes more frequently than KP Northwest. Next slide, please. Now looking into detailed individual group code level comparison, we'll see that there's still a 13% of codes that have significant differences. And again, the magnitude can be very large. If you look at the figure on the right, we additionally added purple. So purple means other type of codes, which includes local codes and things like lab codes and codes that are denoted as other type under the Sentinel Commandant model. It turns out that there's a large chunk of purple at KP Northwest. And we found out that KP Northwest, it actually tends to use quite a lot of local codes instead of standardized medical codes. Next slide, please. Now, in addition to comparing coding between sites, we also want to compare coding across time. So for each individual year, we want to see how the coding have been changed compared to a previous year. This will be very helpful because Sentinel conducts routine data quality check with a lot of manual efforts, but this allows us to do things in an automated fashion. And if you look at the table here and focus on the 2019 versus 2020, you'll see that from within both KP Washington and KP Northwest, we actually observed a relatively larger proportion of code groups that have more differences. Which can be attributed to COVID. So during COVID, there might be a change of health-seeking behavior, and we observed that through this through this automated scanning of coding differences. Another one is the last row, 2016 versus 2017. Again, we also see a relatively larger proportion of coding differences, and one potential reason for that is 2016 is kind of the first year when we adapted ICD-10 coding system. So through this adaptation and adjustment, there might be some differences compared to 2017 when it gets more stable. Next slide, please. Now, I would like to point out to one particular code group. This is called cataract. It's a group of codes. It's an interesting group because we found out that the p-value is very, very small. So that's a significant difference. But the frequency ratio, if you look at the second from the right column, is just 1.03. So that means the magnitude of the difference is actually pretty small. Typically, when you see that from the SCAT test, it says that if you look within group, there will be differences and they're of different directions. So let's look into that. If you go to the next slide, please. These are all the individual codes within the cataract group. So you'll see that there are codes that are in a orange box, and those are codes that are more frequently used at KP Northwest. And there are other codes that are in blue boxes. There are codes that are more frequently used at KP Washington. It turns out that those orange codes are unspecified codes, whereas the blue boxes are codes that are more specific, specifically talking about the location, is it right eye, left eye, or bilateral. So because of such substitution, we saw that significant differences. So the next question is, can we find out a mapping between those specific codes used more frequently at KP Washington to those unspecific codes in KP Northwest? Next slide, please. And that leads to our next component of the project, which is rotation code mapping. And our main method, again, is rotation-based alignment and finding the nearest neighbor based on directional similarity, which is the cosine value. Next slide, please. First of all, data preparation, we of 27,000 codes at KP Washington, 23,000 at KP Northwest. Next slide. And in terms of code embedding, recall that we did parameter tuning. And the way we do that is to measure a AUC that talks about how much agreement are there if I were to use the code embedding to do clustering and compare that to human curated grouping. And we pick the highest AUC, and the corresponding parameter are time window is 1 day. So you calculate code co-occurrence within a day, and the optimal dimension is 250. Next slide, please. So in terms of space alignment, the second column is a summary of the cosine similarity before any alignment. The next column is after rotation-based alignment, and the last column is after projection-based alignment. And if you compare the mean and quantiles, you'll see that there's quite a lot of improvement, which means we did align the two embedding spaces. Next slide, please. Now let's move on to code mapping. Next slide. So we're going to focus on the cataract group that we just showed you. There are 17 KP Washington codes and 15 codes at KP Northwest. Of course, there's some overlap between those codes, and these are all codes that are non-rare. Next slide, please. Here's a matrix of the cosine similarity. There are 17 rows from that are codes in KP Washington and 15 columns that are codes in KP Northwest. The way we conduct mapping is, for example, if I focus on the first row, and that would be E08.36 at KP Washington, then we'll look at this row and find the code from KP Northwest that has the highest similarity as E08.36. And as you can see, that will be the second element, which is E10.36. And we call that a match. And we use this method to go through all the rows. Next slide, please. Recall that we further incorporated code frequency. So on the left is after you incorporate code frequency, and you can see that there's a better distinguish between high similarity and low similarity, and a better clustering pattern. Next slide, please. So here's the mapping result. Without having any knowledge, or even for someone with medical knowledge, it is hard to figure out whether this is a good mapping. Now, if you go to the next slide, we added on the text description. So basically what this tells us is for human being to create a mapping, it will be very, very hard, even if you have subject matter knowledge. But with data-driven mapping, you might be able to do that at scale. So what we're trying to look for are kind of a collapsing pattern where specific codes on the left from KP Washington have been mapped to unspecified code from KP Northwest on the right. And we do see that here, the gray lines are links that have a similarity higher than a cross-validated threshold. The blue lines are the top ones. So like what I said before, from each row, which one has the highest similarity? If you go to the next slide, we also added the purple line, which are the second highest similarity. So you can see that overall, there's a collapsing pattern where specific cataract codes on the left have been mapped to a unspecified code on the right. Next slide, please. So we did some sensitivity analysis looking at comparing different ways of space alignment. And if you click twice, and also comparing different ways of measuring distance. Do we do regression similarity or directional similarity? Next slide, please. The overall conclusion is that the results are not sensitive to how you align spaces and how you measure distances. So because there's a limited time, I won't go into details, and let's move on to how we validate the results. First of all, in terms of code comparison, recall that we found more unspecified code at KP Northwest and more specific codes at KP Washington. We contacted data experts at each site, and we found out that it turns out if you have external providers, they tend to use more specific codes for billing purposes. And turns out within optometry and ophthalmology departments, KP Washington have more external providers, and that leads to the result that at KP Washington you see more specific codes, whereas at KP Northwest you see more unspecified codes. Next slide, please. Here is a simulation study looking at the impact of data heterogeneity and what's the improvement in terms of if you were to harmonize data first before transporting a prediction model. So on the x-axis is the percentage of code mismatch, the y-axis is prediction error. If you look at the black line, that's a line that shows the error if you were to train a model at KP Washington and then directly apply it to KP Northwest. So you can see there's a huge amount of error. Now the blue line is we first compare coding differences between the two sites, and then we correct that, and then transport the algorithm, and that largely reduced the prediction error. Next slide, please. Finally, how do we validate the learned code mapping so that all those lines, those color lines between the two sites? It's actually a very challenging problem because we don't know what's the true mapping between codes from the two sites. But one thing we do know about is that our ultimate goal is to harmonize data. So one way to evaluate how well the code mapping harmonized data is by asking the question of, can we confuse a site classifier after data harmonization? So basically, if I stack individual level data from KP Northwest and KP Washington, where I do that after I harmonize data based on the learned code mapping, then I can send such data to a classifier and ask it to identify for each observation, does this observation or does this patient come from site 1 or site 0? And we're looking for low AUC because low AUC means we did a very good job of harmonizing data based on the code mapping matrix, and therefore the classifier cannot tell, which side the data come from. So next slide, please. If you look at our result, the cross-validated AUC is 0.586, which is a pretty low number. That means our learned code mapping is actually doing a pretty good job in terms of data harmonization. Next slide, please. So in conclusion, next slide. We did code comparison and code mapping. For code comparison, we did find quite a lot of significant differences with large magnitude, and we found out that KP Northwest has many local codes, and there's a potential exchange in the category group between the two category sites. In terms of code mapping, we found that our code mapping methods can collapse specific codes in KP Washington to unspecified codes in KP Northwest. And such methods are data-driven so that they are scalable and potentially less error-prone. And lastly, they're not sensitive to how you align the embedding spaces and how you measure distance. I would like to highlight that all the methods are based on shareable summary data to protect patient privacy. And in terms of implication for Sentinel in the future, I think it's very important to do harmonization before any downstream analysis. So it would be nice if we can develop more methods for semi-automated data harmonization prior to downstream analysis within Sentinel. And also the methods studied in this project can be potentially added to the Sentinel QA package to routinely detect and reduce data heterogeneity between data partners and also across times. With that, I would like to acknowledge my this is teamwork, and we have really wonderful group members from the FDA, KP Washington, KP Northwest, University of Washington, University of Michigan, Harvard, and Duke and Vanderbilt. Thank you, everyone.
Thank you, Shu. That was a really excellent presentation. So this floor is open for question. I think I see one question in the chat. It's more a compliment to Shu. Shu, this was a great presentation. So as people are thinking on questions, I can ask one question to you, Shu, which is really related to the last thing that you mentioned there about the potential utility of these types of approaches in data QA, and which is an issue that really is coming to the forefront as we are thinking more and more about EHR systems, because with claims data, as problematic as they are for several issues that we know, they are at least standard and structured, but the EHRs are more heterogeneous. And so my question to you, Shu, is that how well do you think that these types of approaches can be integrated routinely when you're talking about not just two sites, but many sites at the same time? So what's the scalability of this approach is I guess, my question in a nutshell.
Yeah, that's a great question, Rishi. Thank you for your question. So I looked into the Sentinel QA package. The nice thing is that, first of all, it's a really, really nice package with 3 levels of quality checking. And the nice thing is that it's built upon a Sentinel common data model. So at least we can send generic codes to each site. It will be pretty challenging to implement the methods in this project because it's very, very new methods, and also it relies on pretty complicated procedure. But I do think with common data models, there is a possibility at least to implement the code comparison, because there's essentially scanning through all codes and then comparing coding frequency. For the code mapping method, I think there will be a long way of implementing it within the Sentinel QA package, or more general procedures. Yeah, so lots of work to do in the future.
Thank you. Yeah. So in the meantime, we have received a question from Ryan Hickson. Do you have any ideas about how this type of harmonization could help or hurt in terms of racial ethnic disparities or socioeconomic disparities? For example, some groups of patients may have less access to specialists. So can your method pick it up or help with that?
Yeah, that's a very good question. That also comes to the problem of how do I distinguish, patient difference and practice difference. And I guess your what you asked about, it kind of touches on both. At least one thing I could think of is, when we do those comparisons, we want to adjust for, covariates such as race, ethnicity. And then if we were able to pick up something, one thing I would recommend is to look into what's the source of, the source data, and then what drive those differences. So I think it is possible to detect them. Interpretation of the detected differences can be a challenge, and validation is also a challenge. Yeah.
Great. So I don't see any more questions. I think we have covered a lot of ground in these first 2 presentations, and we have a lot to cover as well. So why don't we break here for quick 5 minutes and come back around to 2:28 or so for the next set of presentations. But Shu, thank you. This was a really excellent presentation with a lot of implications. So thanks.
Thank you very much, Rishi.
Okay, hopefully people had the opportunity to walk around a bit, take a small break. Let's aim to get started as people are still trickling in. So the next 30 to 35 minutes or so, I will be walking you through one of the projects that I had the privilege to lead for the Sentinel Innovation Center, where we developed this process framework, process guidance, nicknamed Principled, which really is in the spirit of the whole activity, where we are trying to put together this guidance where many decision steps along the way, from asking a question to doing the analysis and generating causal inference, are systematically thought through and we are providing some guidance to practitioners on how to approach these decision nodes, the key decision nodes, as they are planning and undertaking this analysis. And of course, Sentinel is our main use case of interest, where FDA asks these questions of regulatory importance all the time, the inferential queries, an association between a drug and an outcome, mostly safety outcomes. So that's the presentation that I'm going to focus on today. So first couple of slides, I really wanted to provide some background on the motivation for this activity. So you are probably already familiar with many other guidance documents that are out there in the literature. There is something called Robbins, for example. There is STAT-RWE. There are best practices documents from the regulators. The NSEP has something. FDA has a couple of guidances. And so the natural question is that why do we need another framework? So if we take a step back and kind of bucket these different guidance documents into specific categories or specific intended use cases, I think it makes it clear that there are various types of tools that are out there in the literature. So you have quality assessment tools. So Robbins is an example. Grace is another example. So these are tools or series of questions, for instance, that you may be able to ask after looking at a study report or a study that is already conducted or published. And depending on the author's reporting on how they did the analysis or design the study, you may be able to assign risk of bias in case of Robbins, for example, if it's vulnerable to some specific sources of bias, for example, confounding or other sources of bias. So these are quality assessment tools. Then you have these reporting tools. So STAT-RWE is an example, Record-B is another example. So these are really highly granular documents which allow you to be really thoughtful about how you plan your study, how you are reporting, transparently reporting and recording all the operational decisions that you have made. So these are more or less protocol guides, protocol development type tools. And then the best practices guidance documents are excellent, but in most cases, they are really can be thought of as mini textbooks. So for example, if you look at the NSEP document, it's more than 100 pages long, I think, and it summarizes all the different types of study designs out there, all the different types of biases that can impact these studies. However, it's really not suitable to kind of guide a researcher through the process of doing a study. It's really a good reference document. And then there are other highly specific ones like the SPIFT, for example, which focuses on fitness for purpose of data. And so and this is of course not an exhaustive list. There are probably other documents out there. However, after kind of reviewing the field, what we saw for the FDA was that there are various tools, but there is nothing that offers a general framework to guide decision-making at various steps when designing a study with the intent to make causal inferences, which is what Sentinel does all the time, of course. So that's how we define the vision for this framework to guide principled investigations for drug safety or effectiveness outcomes using healthcare data. This is a stepwise process that systematically considers all the key choices with respect to design and analysis that influence the validity of these types of studies. The standardized process that is outlined here is meant as a guide to inform conduct of these types of studies. However, it's not meant to be some kind of a rule book of sorts. This is simply a guide, things that researchers can think about as they are going through the process of designing and conducting their own study. And there are the 3 bullet points to the bottom here are really important for us as a motivation. So as you might imagine, there are plenty of different investigations that occur with the inferential intent in Sentinel in a given year. And these are undertaken by various investigators. So there are bound to be variations in practice in terms of how these investigators approach these types of studies, which is fine. Everybody's making the best call for their own research question. However, if we outline a general process, we can somehow streamline this process and limit variations, which is kind of one of the major motivations here. The focus is on repeatability of the process. And then we also were quite cognizant that we did not want to write something which was just thought of by a bunch of Sentinel investigators. We really wanted this to represent the state of the art in the field. And so it was important for us to have this written and endorsed by independent experts, which is what we did. And so hopefully these two slides make a good case for a general framework that we ended up developing through this principled process, which we feel really is an addition, definitely for the Sentinel program on how Sentinel will conduct its investigations. But also, I think more broadly, it's an important addition to the literature because it has the potential to inform or at least systematically approach these decision notes that you go through when you design a study with a causal intent. Okay, so I'll start with the overview of the process, and then we can dive deeper into each of the steps that are proposed. So this is how the overall process looks like. So of course, this is a dense slide. There's a lot going on here. So I'll walk you through what this is, and then we can break it down into various steps. So as you will see here, this is a 5-step process. Step 2 is 2A and 2B, so really 6 steps. And then there is a clear demarcation here between the study planning and inference phases. So in the study planning, what we're saying is that you have the ability to specify your question, to specify all your design choices, identify a suitable data source, do some preliminary investigations around precisions and diagnostic evaluations, and specify your robustness evaluation plan, all as a part of your study planning. So up to step 4, there is no formal analysis is conducted. There is unblinded, meaning that investigators or analysts haven't yet, through the first 4 steps, peeked at the association between the exposure and the outcome of your interest. And this is quite important because you want to make choices that are objective. And so you don't want to inject subjectivity in this process by looking or having some sense of what your results might show, which could lead to specific choices, which is not obviously scientifically ideal process. And so that's the demarcation between study planning and inference, and I'll get into how we kind of intend or advise to achieve that. And then the second point I wanted to make on this figure, the overview figure, was that this process, as we considered it, it's not a linear process. So it's not going from step 1 to step through step 5 in a linear way. There is some back and forth going on, for example, as you see here in step 2, which basically means that when you kind of come up with a question, or when you're faced with a question and you are making these design choices, there are situations where you will need to consider carefully the data source that you have availability to. And then based on what you have available, you may need to tweak your design choices a bit. And so that's the relationship between the emulation of the trial protocol. So that's the protocol writing and the fitness for purpose. And again, we'll go into more depth there, but just wanted to highlight that we have considered this process or allowed this process to be somewhat circular. And you can also see this at these stop signs. So these are exit ramps for some of these steps. So if you're not able to kind of get to a place where you want to get to after end of the second step, for example, you may be able to go back to the first step and reassess the question in this example. And so I hope that it provides you with a good sense of what we are trying to achieve here, but I think that it makes more sense once we start talking about each of these steps. So let's move on to some of these steps. So the first step to any activity that is intended to generate causal inference is asking a well-defined causal question. And over the last 5 years, you probably may have come across this term of target trial approach or target trial framework, where you really have the ability to explicitly ask a question using the data sources that you have at hand by envisioning how you would study this question if you were to do this prospectively in a randomized trial setup. And so we think that this is a really useful device. The target trial protocol framework is a really useful device as a starting point to ask a question that is transparent and answerable using the data elements that you have access to. And so this is really an example of a target trial table, which really outlines all these elements. On the left, you see the exposure or treatment strategies, your assignment, your eligibility criteria, and so on, and how you would envision them in your target trial if you had unlimited time and resources to pursue this. But of course, that's not the case. So you are kind of relying on these real-world data sources to emulate these trials. And to do so, you need translation of these design elements that you outline in each of these cells using the healthcare data sources. And this is just an example of really transparent way to ask a well-defined causal question and then outline all your assumptions in a way that is really tied close to each of these design elements that you are trying to achieve here. So, for example, follow-up start, time 0. It's quite important for these types of studies, and many studies kind of trip up in these decisions. And so, if you use something like this, which is very transparent and thoughtful, you are likely to kind of guard your study against these avoidable pitfalls of observational studies. So step one, again, not a rocket science, is really approaching this from a framework of the target trial, which we find to be quite useful and practical device to ask causal questions. So that's our step one. So once you have step one, once you have a causal question, then you can move on to really, because that's just a first step. You can then move on to the second step of really outlining how you are operationalizing all these design choices. And that's your step 2A, where you are describing emulation of each of the elements or components of that protocol, of that table that you just saw. And then, as I was saying earlier, you also want to be closely mindful of the data source that you will need to successfully emulate these components. And so I think the emulation protocol and the fitness for purpose of data source go hand in hand, and they are actually informed by one another. And so that's why you see a circle there. And I'll get into the process that we are outlining for fitness for purpose data, how you get to a place where you start making some decisions around whether the claims data are enough, for example, or you may want to augment it with something else like an EHR or some sort of registry. And so that's the step 2B, is identifying fitness for purpose data. And so if you focus for a moment on the right-hand side of this figure now, there will be circumstances where you may not be satisfied with the data source that you may have at hand for emulating the trial that you want to emulate. So in this situation, you may want to stop here and reassess the question, the causal question that you asked in step 1, and maybe you want to frame it slightly differently in a way that is still meaningful, but it's addressable using the data source that you have at hand. So that's the exit ramp, as I was describing. However, if you are satisfied with your entire protocol, and if you think that you have a fit for purpose data to address or conduct this investigation, then you may want to consider protocol registration at this step, which is quite important and a concept that is really gaining a lot of steam in the epidemiology community over the last 5 years or so. And this is really crucial because you want to avoid any subjectivity in the process by looking at the data and deciding on or changing your study question or some design choice in a way that is kind of more favorable to the result that you may want to see. And so to protect the objectivity, I think it's important in some form to consider protocol registration once you have the full outline of the protocol. And then we, of course, have some guidance on that as well. So let's move on to more detailed description of the steps 2A and 2B. So 2A is really where a lot of the work exists. So this is where the protocol templates like Start RWE, for instance. There is a newer one called Harper by an ISPOR-ISP group, also led by Shirley Wong. These types of documents provide really detailed guidance on how to document these operational decisions. So we did not want to reinvent the wheel here. We refer users to these pre-existing documents, but we want to explicitly involve or include this step in the framework, because I think it's quite important for any study that you do. A transparently recorded study protocol is something that you will always need. So that's your step 2A. Step 2B is something that we are kind of introducing here. A guide for identifying fit for purpose, or how you approach fitness for purpose of a data source when you are considering these types of studies. So again, it's a fairly dense figure here, but it's based on the FDA draft guidance to the industry, which was published here in 2021, which frames the question of fitness for purpose into two broad bucket. So there is the data relevance assessment, and then there is the data reliability assessment. And the data source that meets both of these are considered, or can be considered, fit for purpose data. So data reliability assessment is fairly intuitive to understand, and gets at the concepts of accuracy of data, completeness of coding, for instance, provenance, traceability. And these are the concepts that we have always paid close attention to in Sentinel, and we really have moved some of this upstream when we convert these raw source data to the Sentinel common data model, where we have, as Shu was also mentioning, we have dedicated QA packages to check for completeness, for instance, of coding, and pay close attention to traceability of where each element is coming from in the Sentinel common data model. So that part for Sentinel is more or less addressed, but the data relevance assessment, I think, is going to be quite crucial for us moving forward, because the IC is, so Sentinel currently has a large insurance claims Sentinel distributed data network, which involves millions of patient identifiers, and really the backbone, the workhorse of the program, where most of these questions get asked into the Sentinel distributed data network, which is entirely claims-based. However, the IC is already developing, or has made substantial advances in developing or bringing in more EHR-based assets. And the question for us is going to be, moving forward, is when do you activate this EHR-based network? Because the pro for the EHR-based network is they are likely more granular in terms of clinical capture of some of these variables of interest. However, the con is that they are not large enough for us to conduct, in many cases, these standalone investigations. So in some ways, we have to kind of consider the two systems, and this is what this figure is getting at. So we always start with insurance claims data, because that's our largest asset. That's the workhorse of the program, and ask these questions regarding the ability of the insurance claims data to capture key elements for your study. And that includes the eligibility criteria, the outcome of interest, the treatment or exposure of interest, and then key confounding variables. And so each of these questions can be answered yes or no. And then if you answer yes, you can stay in the insurance claims box. But if you answer no, then you may want to move out from that box to think about how best to incorporate additional sources into your study. That includes EHR, that includes some other data sources like inpatient EHRs, large inpatient EHRs that Sentinel has access to, for instance. And so I think this is really a way for us to methodically think about when to make best use of this budding system that we are building for Sentinel, because there are potential advantages and potential challenges in using them. So this is really our way to formalize our thinking around that process. And eventually you will want to get to a place where you either by insurance claims alone or by incorporating some additional data sources, you answer yes, or you get to a place where you are able to somewhat confidently say that these key concepts are measured well, either alone in the claims data or in combination, some combination of using EHR, and then you can kind of meet these basic requirements for data relevance. The relevance for the FDA guidance document also involves the initial feasibility assessment. So here you may want to conduct some basic checks on how many number of patients are there using a drug of your interest, for instance, really high-level checks to basically avoid wasting time of developing the whole thing and running the whole thing and then finding out it's not enough patients. So basic feasibility check is a part of data relevance assessment. So once you establish the data relevance and reliability, these data sources alone or in combination can be considered fit for purpose. So this is our kind of more formalized way of thinking about fitness for purpose in the context of Sentinel, but again, it's broadly applicable to other settings as well, I think. So once you have the steps 2A and 2B addressed, you may want to consider protocol registration, as I said, if you are satisfied with both of those things. And then once you have protocol registration, once you lock all your choices, all your major choices regarding design, you may then want to approach the data in a principled way to do some basic checks on the data, so to speak, which involve assessment of expected precision and diagnostic evaluations. And the reason why this is unique, I think, for observational studies is that you have the ability to make study adaptations that are guided by some of these things that you may see in your data. However, you don't want to do this in an ad hoc way that could include subjectivity in your assessments. And so we are providing some detailed guidance or at least a way to approach this. I think there is really limited guidance on this specific issue on how much to what extent you can go to without calling it analysis in the observational data space. And that's what we are trying to get at here. Please remember that this is a step that follows the protocol registration. So again, to preserve the objectivity in this whole process. So step through. So once you have the step 2 completed, which has your protocol for target trial emulation and your fitness for purpose data source assessment complete, and you're satisfied, you may move on to the data source that you have access to and start assembling the study population. And this might involve implementation of eligibility criteria, assignment of individuals to treatment groups, so how many patients you have in your exposure groups. And once you have the study population assembled, you may want to move on to do some expected precision calculations. And this is really important for us to keep in mind that whatever we are suggesting here, this is based on the outcome counts in the overall study population without stratifying by treatment. Again, to preserve the objectivity in assessment here, we don't want to kind of take a peek at how many events are happening, what the event rate in each of these two groups are. And to avoid that, we can do this in a population where you have the outcome counts for the overall population, not stratified by treatment. And there are methods established, for instance, published by Rothman and Greenland here to do that. So this will give you an assessment of what is the expected length of your 95% confidence interval is, for example. And if you think that that's achievable or desirable, I think you can move on. But if not, then you may want to go back to step 2 and consider some design modifications. Maybe your inclusion criteria are too strict. Maybe you want to broaden that out. This is important to keep in mind that these are study adaptations that are still principled because you have a trace for what you decided initially and what you approached, how you approached the data source and what you observed there. And based on that, what is the adaptation that you are making? And this is the protocol registration gives us this traceability of these steps. So again, the spirit here is to stay transparent, stay principled, but still allow the flexibility, which I think will be quite common in observational settings where people may want to make study adaptations based on their existing data or available data. So that's the guidance on the initial feasibility assessment side. The other thing that you can also do is diagnostic evaluations. And this is something that we are all very familiar with. We do this all the time. So once you have the study population assembled, you look at the distribution of baseline characteristics. And this is really a way for us to get at the core causal inference assumptions. So the first one, the general description or distribution evaluation, is getting at the exchangeability assumption, for instance. Similar thing with the evaluation and informative censoring. You want to get a handle on whether the two treatment groups that you have are truly comparable or not. So this gets at the concept of overlapping populations or clinical equipoise, for example. There are also analysis-specific things that you may be able to do. So for instance, if you're using propensity score-based analysis, you may want to evaluate balance conditional on the propensity score, which is a mechanism for a diagnostic for PS model specification, for instance. If you're using weighting model, you may want to look at the distribution of the weights over time as a diagnostic for weight model specification. So these are all really approaches that you may want to kind of finalize in a way before conducting your final analysis, because you don't want to be in a position where you have kind of seen your final results and then you may realize something was off in the propensity score model, so balance was not achieved, and then you may want to go back, may have to go back and fix some of those things, and that could again introduce subjectivity in the process. And so most of these diagnostics we think are solvable by altering or refining these models that you're building. But in case they are not, then you may want to again go back to your step 2, where you may want to study a different comparison group. For example, if you find out that these patient populations are entirely non-overlapping or non-comparable. However, in a more happy ending, you have situations where you have fairly confident assessment of your precision, where you think that the desired precision is achievable and all the diagnostics are passed. Then you may move on to step 4. And the step 4 here is the detailed reporting on robustness assessment or pre-specification on all your robustness assessments. So these are your sensitivity analysis, basically. And the way we are thinking about this is really a high-level overview of what are the types of sensitivity analysis that one may be able to consider. So there are deterministic sensitivity analysis that you always consider for all these studies. These are varying design choices, in most cases one at a time, for example, or analytic choices one at a time. There are also more probabilistic or quantitative bias approaches, which are frequently used. There are more and more upcoming net bias assessment type of approaches, for instance, negative or positive control analysis, the trial calibration approach, for instance. So these are all things we think can benefit from pre-specification before running the final analysis. And the reason is that you, once you know the results, it's kind of easy for you to choose your parameters, for instance, in the quantitative bias analysis, which may make the results look more robust than they actually are. And so if you pre-specify, you hang your hat on all these assumptions, all these analysis, additional analysis that you are conducting, it again provides more room for objectivity in your decision making when you do run that final analysis and you do run these all these analyses. And so step 4 again is robustness evaluation. So once you have these 4 steps, we do recommend consider logging the outcome counts, which you generate as a part of your step 3, as well as all the diagnostic evaluations of model fit statistics, for example, as well as the robustness assessment as an amendment to the protocol that was registered at the end of step 2. And again, the spirit here is to stay transparent. Even if there were situations where you had to make study adaptations, you want to have a trace on why these decisions were made. And that's a mechanism for doing that by doing the first phase or a main primary protocol registration and then updating that protocol if needed to log your choices or modifications that you have made. This is actually quite similar in principle to how these adaptations are thought of in the prospective randomized trials, where you may have challenges in recruitment for some inclusion criteria, for instance, after the protocol was registered, and then you may decide to lessen those restrictions and to meet your recruitment goals. And so these are logged as protocol amendments, which we see very frequently. And so I think the parallel that we wanted to draw here is that for observational studies, this is still an acceptable practice as long as you have a trail or you can trace your decisions. And so that's the spirit of providing these stepwise guidances for each of these decisions that investigators face when they design their study and decide to analyze their study. So that's the first 4 steps. We still consider all of these study planning, although there is some basic model building that's going on in step 3. It still can be considered a step of planning, because you are trying to make sure that you are ready with the final modeling choices when you want to go ahead and push that button for your final analysis, which is step 5. So our thinking here is that once you have done your due diligence through the steps 1, 2, 3, and 4, step 5 becomes really easy, because then you really are running the analysis that you have specified and spent so much time thinking about in terms of the diagnostic evaluations, in terms of the desired precision estimations. And so you are able to conduct this analysis and then make objective inference based on all your assumptions that you've pre-specified through steps 1 through 4. So that was my last slide. Actually, I wanted to give a big shout out to the entire working group and our advisory committee. This was a large group effort, more than 20 of our group members across 7 or 8 institutions. And so this is a manuscript that is undergoing internal review right now. And we hopefully will be able to put this out there later in the year. But I will be very happy to take any questions or comments on this. And this was my last slide. I'm also happy to take questions on email, which is listed here. Feel free to post your questions in the Q&A feature. Your lines are muted. Okay, hearing no questions, I think we can move on. But as I said, I'm happy to take any questions or comments. Oh, actually, we just received a question from an anonymous attendee who asks that there are similarities of this work to the RCT duplicate. So yes, this is very true. So RCT duplicate actually was a really great learning experience for many people involved, both at the Brigham as well as the FDA. And many of these steps that are kind of crystallized here are informed by our experiences while working on RCT duplicate. So yes, it is very true. RCT duplicate was more focused on emulating the trials and getting the concordance or understanding the reasons for discordance between those estimates. But here we took a step back and thought of the process that we followed, and the process that I think will be useful for Sentinel to follow as we think more about these protocol-based assessments in not only claims data, but also bring in more and more EHR data. So yes, there are many similarities here. A lot of this is informed by our experience conducting the RCT duplicate project. Okay, thank you for your question, Sarangan. If there are no more questions, I will like now to turn over to my colleague, Dr. Weberpals. Janick, are you able to unmute yourself? Okay, perfect.
Sure. Cool, okay. So I'm excited to present today on behalf of the Sentinel team, who has spent quite some time and brain power in finding methods and systematic approaches to an old but yet unresolved problem, which is missing confounder data. Next slide. So these are my disclosures. I was a prior employee at Hoffmann Roche, and I held shares in Roche. Next slide. Next one. So claims data have been the backbone for real world data studies for a long time and are very rich in information. Yet there are very detailed variables that may be of high prognostic value for the outcome that we're studying, and that we would like to adjust that in our analyses that live in electronic health records. And examples for that are labs, vitals, disease-specific data, such as cancer stage or biomarkers, since I'm also very involved in like cancer research. So this is something that I have was a challenge also to my research for a long time. And also things like lifestyle factors, smoking and alcohol. And typically, we don't know why for some patients the observations are missing and for some not. It could have different data generating mechanisms in the background. For example, the physician did perform or not order a certain test for a certain patient for whatever reason. Certain measurements are just collected for particularly sick patients, or maybe the information is hiding in unstructured notes, for example, clinical notes, which then relates again to the first presentation that we heard today. Next slide, please. So for these very classical examples of partially observed covariates, there are established missing data taxonomies dating back to Rubin's inference and missing data work, which probably most of you have already heard of. And that can relate to, for example, missing data mechanisms, so missing completely at random, and not at random, as well as missing data patterns, which can be monotone or non-monotone. However, there are still quite some challenges to make use of these taxonomies for our work in causal inference. For example, the textbook definition of missing not at random is often not very helpful in causal inference, since in textbook, it's often just written that MNOR is anything that is not missing completely at random or at random. In addition, something that we haven't thought too much or haven't given too much thought in causal inference is how do any of these mechanisms relate to bias, given the strength of the correlations between exposure covariates and outcomes in high-dimensional database settings, such as, for example, database linkages. Are we able to recover the information, or are we completely lost if something is just partially observed or not? Many siloed approaches have been proposed, but there's been not too much guidance on like really systematic end-to-end approaches like we are using causal inference when we in the beginning draw our assumptions using, for example, causal diagrams. We consider confounders, unmeasured confounders, instruments, treatment effect modifiers, or colliders, and we should do the same also with missing data. And so this is essentially the aim, the bigger aim of this work stream, is to integrate Rubin's framework with multivariate missing data under causal exposure outcome relationships. And this is something that I would like to term as structural missing data assumptions. So what we would like to do on a high level and in short is that to ask the question, how can we integrate missing data into our causal inference workflow and establish principled and a systematic approach to partially observed variables? Next slide. And so the development of the methods for these aims, has been carried out at Brigham and Women's Hospital using a deterministic linkage of the MGB electronic health records linkage to Medicare, and also using comprehensive simulation and base case studies. And so the findings of the theoretical results in these missing data simulations have funneled into something implementable and operationalizable toolkit, which I will go into more detail later in this presentation, which we are currently in the process to transferring to our testing site at Duke University for it to be like evaluated, to resolve implementation glitches, and to be tested and validated there. Next slide, please. So for aims 1 and 2, we conducted comprehensive plasmode simulation based on an exemplary diabetic cohort. And so for the study design in detail, from a deterministic linkage between the EHR of the Mass General Brigham hospitals in Boston and Medicare, we identified an empirical cohort of diabetic SGLT2 or DPP4 inhibitor initiators with a cohort entry date defined as the first use of either of the two drugs. The exemplary outcome we looked at was the time from index date to a composite cardiovascular outcome, including MACE, heart failure, and death. And covariates were ascertained in a baseline window of 180 days before and including the index date. And so from this empirical cohort, we identified 3 sub-cohorts for our simulation, for which we had complete information on the HbA1c values, body mass index, and smoking history, respectively. And so for these 3 confounders, so HbA1c as a continuous value, BMI as an ordinal value, and smoking as a binary value, these were the covariates or the confounders that we defined as the confounders of interest in this plasmode simulation. Next slide, please. So using this plasmode simulation framework, we simulated 100 data sets of 1,000 patients each for each confounder of interest cohort using a stratified resampling approach. The desired simulated treatment effect between the exposure and the outcome in this simulation was defined as a hazard of 1, so a null treatment effect. As part of the outcome generating model, we selected the confounders of interest and 25 additional covariates that we used for the outcome generation, and which I will refer to as C1 covariates for the remainder of the presentation. In addition, I will refer to all other variables which were not part of the substantive model as C0 covariates. Next slide, please. So to introduce missingness, we first outlined 4 most realistic missingness mechanisms based on Rubin's missing data mechanism framework, which are depicted here as so-called M-graphs, which are logical extensions of causal diagrams. And so the M-graphs illustrate here no causal effect between the exposure E and outcome Y. C1 are the aforementioned true confounders, which show a natural correlation with our fully observed confounder of interest C. So this is either HbA1c, smoking, or BMI. And the product of C and the missingness M is C observed. Next slide, please. So to go into a bit more detail here, in the simplest scenario, the missingness M was not associated with any other observed or unobserved covariates. And this was then defined as the missingness mechanism missing completely at random. And so this was simulated by randomly setting some values of our confounder of interest to missing. Next slide, please. Under a missing at random assumption, the missingness was dependent on the observed C1 covariates. And we simulated missing at random by defining the missingness probability of C as a linear function of the values of C1, where in this case, every C1 covariate had the same weight. And patients with a higher weighted sum score from this linear model had a higher probability to have a missing confounder of interest. And this is why it's missing at random. Next slide, please. So under a first missing not at random scenario, we had 2 in total. The missingness probability only depended on the value of a true unobserved confounder, which in this scenario was H. So it was part of the missing data of the outcome generating model, but which was dropped then for all of the subsequent analyses and hence unobserved to us. And since the missingness here depends on an unmeasured confounder, we call this mechanism MNAR unmeasured. And since H is the true confounder in this case, the resulting missingness is not at random and very likely differential according to our assumptions. Next slide, please. So one special feature of this MNAR unmeasured scenario is that if there are other covariates which may be not considered for the substantive outcome model, but which are highly correlated to U or to the confounder of interest, including such covariates, which we often term auxiliary covariates, into the missingness diagnostics, which I will talk about in a second, and into the imputation models may be of high value as it enables us to make this MNAR unmeasured scenario look much more like a missing at random scenario. And so examples in our simulation where, for example, diagnostic codes for smoking or smoking-related diseases such as COPD, which could serve as appropriate auxiliary covariates for smoking, which is our confounder of interest. And so these auxiliary covariates could come, for example, from from the covariate vector, which I referred to earlier as the C0 vector, or the C0 covariates. Next slide, please. So lastly, in the second missing not at random missingness scenario, the missingness solidly depended on the true value of C itself, but nothing else. And this is why we call this MNAR value. And this is typically considered the most difficult missingness mechanism, since we have neither observed nor unobserved factors that influence the missingness, but it's really just based on the value of the confounder that we're concerned of itself. Next slide, please. And so to make the simulation as realistic as possible, we not only varied the confounder of interest, or the variable type of the confounder of interest, and the missingness mechanism, but additionally other simulation parameters such as the proportion of missing values, the inclusion of auxiliary covariates, as well as the presence of heterogeneous treatment effects between the confounder of interest and the exposure. We additionally investigated also how analytical approaches downstream, such as complete case analyses, inverse probability weighting, missing indicator approaches, and various single and parametric and non-parametric multiple imputation approaches would perform in all of these scenarios. Next slide, please. And to check how potential structural missing data investigations would perform under these scenarios, we defined 3 group diagnostics. And so the first group diagnostic would investigate in more detail the distributions of patient characteristics, of baseline patient characteristics between patients with and without the observed confounder of interest. And so for that, we first would compute the absolute standardized mean differences of baseline covariates, and adapting the logic from, for example, balancing scores that also Rishi talked about earlier in propensity score analyses. We would also define then, for example, absolute standardized mean differences below 0.1 or 10% as that there's highly balanced, that these covariates are balanced between those two groups, and above 10%, they would not be balanced. If they were balanced, this would more indicate a scenario which would be completely at random, while if we saw some patterns, this would be more indicative of a missing at random mechanism. And following the same logic, one could also formalize that into a formal hypothesis test, and this is what Hotteling and Little did. Hotteling's test is a multivariate t-test that tests the distributions of patient characteristics in both groups, while Little has kind of a global test for missing completely at random. And so by rejecting the null hypothesis, we would infer that there are differences in the patient characteristics between those two groups, which would be, again, indicative of a missingness mechanism, which would not equal to missing completely at random, but more likely missing at random or not at random. Then in the group 2 diagnostics, we would fit a classification model. In our case, we fitted a random forest model, since this has also some other advantages in this case, and looked at if, based on all of the observed covariates, or also in addition to the C1 covariates, we could predict the missingness indicator. So just the confounder of interest, or the presence of the confounder of interest, if this could be predicted. And values around 0.5 would indicate a random prediction, which would rather be indicative for missing completely at random mechanism behind the data generating mechanism, while values meaningfully above 0.5 would indicate strong correlations between the observed covariates and the missingness, and hence would be more indicative of a missing at random assumption. Then lastly, in the group 3 diagnostics, we would check if the missing indicator would be associated with the outcome in a univariate model, but also in an adjusted model conditional on all other prognostic factors. So if we hypothesize that the underlying missingness mechanism is missing completely at random, we would probably assume that there's no association in neither the crude nor in the adjusted model, since the missing is completely at random. Under a missing at random assumption, we would hypothesize that there could be an association in crude, but not in the adjusted model, because we would condition on all other observed covariates. Under a missing not at random mechanism, we would assume that there would be probably meaningful differences both in the crude but also in the adjusted hazard ratio, which would be more indicative of a differential missingness and hence missing not at random scenario. Next slide, please. In terms of evaluating the imputation and downstream analytics, we looked at various metrics, but our main metric here was the root mean squared error as the best compromise between bias and variance in the ability of the different models to recover the true treatment effect, which was in our case a null treatment effect. Next slide, please. So looking at the interim diagnostic results here across all scenarios, we found very interesting patterns in terms of the missing data diagnostics for each mechanism. So while the distribution of patient characteristics seemed very balanced and missingness not very predictable nor differential in in the true missing completely at random scenario, there seemed to be notable differences in the distributions of patient characteristics under a missing at random scenario. And while the univariate group 3 diagnostics here indicated significant differences in terms of the outcome between patients with and without the observed confounder of interest, this spurious association was adjusted away after conditioning on the C1 covariates, which seems quite reasonable, as these are the ones that were used for the missing data generating model and were also, in addition, fully observed. So for both missing not at random mechanisms, the group 1 and 2 diagnostics, on the contrary, were more difficult to distinguish from missing completely at random and at random. However, something we observed was that for both missing not at random mechanisms, there seemed to be a much clearer tendency for a differential missingness association in the 3 group diagnostics in both the univariate and the adjusted model. So this result became actually even more apparent when we calculated 95% confidence intervals using the Monte Carlo errors as opposed to the more conservative standard errors that we used as depicted in this slide here, which resulted in wider confidence intervals. And so the composition, or looking at all 3 group diagnostics here between those missingness scenarios, made us feel more confident that we could get an idea about the likelihood of one missingness scenario being more likely than the other. Although in total, we found that especially MNAR value was, if you look at the diagnostic results, seemed to be very close to missing completely at random. And hence these 2 missingness mechanisms may be in a real world example be most difficult to differentiate. Next slide, please. And so we found these results also to be very stable and consistent when we stratified those results across confounders, meaning that here the variable type of the confounder of interest, of the partially observed confounder of interest, very likely has no influence on the missingness diagnostics. And if we look at the next slide, we also see the same pattern here with when we stratified the results by proportion missing, with the exception that the random forest-based group 2 diagnostic here, the area under the curve, even increased in its ability to predict the missingness with the higher missingness proportion, which is relatively common for prediction models if the outcome or the predicted like target parameter has a higher prevalence. Next slide, please. So on the downstream analytical task, we observed that multiple imputation approaches based on multiple imputation by chained equations algorithms performed here the best in recovering the true treatment effect estimate. And this seemed to be especially true for the non-parametric random forest-based multiple imputation approach, which was largely explained by the better performance in scenarios with heterogeneous treatments effects, which we did not specifically model in parametric imputation models to look at those differences. But as you can see here, the differences between the default parametric imputation approaches for the respective variable type and the random forest-based imputation model was not too large. Next slide, please. Something that is probably quite unsurprising to all of us is that we observed a rather worse performance in missing not at random mechanisms, particularly if the underlying missingness mechanism followed an MNAR value mechanism, as we already assumed. Next slide, please. And also, just to round this up, also unsurprisingly, the error increased with a higher proportion of missing values. Next slide. And so before I come to the end, I want to stress that, as also Rishi mentioned in his presentation before, the importance also of considering sensitivity analyses to check the robustness of the analytical decisions that we make, and to also already a priori outline this in your protocol, which now you could do with those missingness diagnostics and having some kind of an idea about the potentially underlying missingness mechanism. And so also here, sensitivity analysis should be part of every analysis involving missing data. And as we have observed, particularly MNAR value mechanisms are the hardest to differentiate against missing completely at random and missing at random in terms of the missing data diagnostics, and also in terms of the error that is produced by MNAR value, as this mechanism is much more susceptible for much stronger bias. And hence here, sensitivity analysis would make particularly sense. Next slide, please. And so this is where quantitative bias or tipping point analyses can be also extremely helpful for missing data investigations. And in determining if under a wrong missing completely at random or at random assumption, the global conclusion would change if the true underlying missingness mechanism would be MNAR value. And so the example illustrated here in the figure was not part of this plasmode simulation, but depicts a scenario where, for example, H would follow an MNAR value mechanism. This would mean that, for example, here we would observe systematically higher or systematically lower H values among those with missing values in H. And in this case, we would have trouble imputing this data if this information was only dependent on the value of H itself, but on nothing else. And so under a sensitivity analysis that is often referred to as a not at random fully conditional specification analysis, this systematic difference could be modeled using a sensitivity parameter delta, which reflects the systematic difference in those H categories or in those H values between those which are observed and which are not observed. And so if under a realistic range of delta parameters, which you can see in the graph on the x-axis, the conclusion of the main analysis, so in this case, the hazard ratio on the y-axis, would not change. This would give additional confidence about the robustness of the main analysis. And so in this case here, you could see the point estimate and the confidence band would cluster around the true hazard ratio, which would give us around the true hazard ratio, which would give us more confidence, as in no of these scenarios, the upper confidence interval, for example, would touch or cross the null, which would mean that we would need to reject what we found in our primary analysis. Next slide, please. And so lastly, to enable researchers to implement the 3 group diagnostics that I presented today on a routine basis, potentially already at the study design level, the resulting deliverable of this workstream is a toolkit in the shape of an R package called Structural Missing Data Investigations. That was designed for exactly this purpose, as implementing all of these 3 group diagnoses can be quite tedious to do. And so this package really kind of enables everyone to do this very conveniently. And so under the given URL that you can find here, you can find the related website of the software release, which is deployed on our GitLab instance with some very useful tutorials on the functionalities and the use of the package. And just as a disclaimer, the package is still in beta testing and will be validated at the testing site at Duke University, as I mentioned in the beginning. And after the testing phase, we plan to ship and make this package available then on CRAN. Next slide, please. And so just to round this up, we think that this package integrates very well into the ecosystem of other missing data packages into our routine causal inference workflow, as depicted here in this graph, and can help establishing a systematic and principled approach and workflow to handling partially observed confounders. And so this is just an example on how such a workflow could look like. So let's assume we have a data set with missing values. We could use the SMDI-R package to visualize the missingness that we have in our covariates, and also check the assumptions based on the 3 group diagnostics that are presented today. If the assumptions would allow, and there are no particular concerns against, we could impute the missing data using, for example, the mice-R package, which would create multiply imputed data set. Using the match-them-R package, we could then establish our routine propensity score workflow by matching or weighting the each imputed data set, and also assess the balance on the matched or weighted data set on each imputed data set, analyze each of the matched and weighted imputed data set, and then pool the causal effect estimates, which would give you then just one treatment effect estimate, as you would have also observed without in case you would have followed this workflow without missing data. Next slide, please. And so, of course, this work is a team effort, and I would like to highlight and thank this wonderful team from Kaiser Washington, Duke University, Harvard Pilgrim, and FDA, who have been working here on this project. And want to thank them, and also thank you for your attention.
Okay, great. Thank you, Janick. That was a really comprehensive overview of your work. So this presentation is now open for questions. If anybody has any questions for Janick, please feel free to drop them in the Q&A feature. And as people are thinking about questions, Janick, one question that I have for you is, what do you think that this is going to look like for a real case example? So your simulation results are quite interesting and convincing that these diagnostics that you have developed are doing their job or working as intended, but how do you see this playing out in real case examples?
Yeah, true. So in real case examples, of course, in the simulation, it was easy because we knew the underlying missing data generating mechanism. But I think if we look at the composition of all 3 group diagnostics, this could really give us a bit of a flavor. So by theory, we will never be able to recover the true missingness mechanism unless we know the true data generating mechanism behind it. And this is how, for example, expert knowledge and quantitative assumption testing, as we've done here, could flow together and give a reasonable or give analysts some more power to make reasonable assumptions about the underlying missingness, and also more evidence, as for example, just stating we assumed MAR, and that's why we imputed. So this gives this much more like a substance to our assumptions, which is something that we always want to do in causal inference. And of course, this package or these diagnostics still need to be validated, but we have some base cases inside, and this will also be published along with the simulation paper.
Great, thank you. Makes sense. So we have a question from Ryan Hickson. He is wondering about your results, where you see multiple imputation was the best performing method with respect to root mean square error. So did you investigate any simpler stochastic imputation approaches? Because multiple imputation sometimes can be difficult to implement or cumbersome with various software packages. And so any insights into any simpler mechanisms or imputation approaches?
Yeah, so we not only looked at multiple imputation, but also single imputation approaches. We found that those also work quite well, not quite as well in all of the scenarios like multiple imputation approaches, which makes sense because in multiple imputation approaches, you have many advantages. For example, that you not only quantify, for example, in your variance estimation, the error that is caused just by the usual sampling variance, but also caused by the missing data itself. This makes multiple imputation quite appealing, but we also looked at single imputation approaches, also based on a random forest model, which actually also worked quite well.
Hey, are there any more questions for Janick or on this presentation? Okay, hearing no questions, I think we can go on to the last closing remarks, which I'm happy to provide on the behalf of Innovation Center. So really wanted to thank each and every one of our presenters today for their excellent comprehensive presentations, which took years to conduct, and it's really hard to kind of articulate how many complexities and how many tricky situations each of these project teams faced and encountered. So it's really really impressive amount of work. I should also thank all the attendees who really asked excellent questions towards the end for each of these presentations. So thank you for your attention and thank you for your interest. I should note that the 4 presentations that were presented today are really a small sampling of the Innovation Center projects that are ongoing and completed. So we have a large portfolio. Over the last 3 or 4 years, we have a large portfolio of 20+ projects that we have initiated and completed in some cases. And so this is really a small sampling of some of the learnings that we have accumulated over these years. As you saw from the presentations today, we are really broad in terms of types of questions and types of methodological issues that we are covering, right from more sophisticated machine learning type approaches. They're highly innovative and throwing those methods at real problems that require some solutions, like the data heterogeneity, which have really not gained as much attention as some of the other problems, to the other spectrum where we have the classic issues of missing data, for instance, which have received a lot of attention, but not really keeping the use case in mind for that is specific to Sentinel and many other investigations that focus on an association between a treatment and an outcome. And so this is really a broad set of projects, and we are accumulating learning. We are also actively trying to make learnings widely available for the community. So for example, Janick described the package that he has developed as part of his project. So our attempt really is to generate as much knowledge as possible, but not only that, we are also actively seeking to disseminate this knowledge and hopefully building on that with engagement from the community members. And so really wanted to thank everybody involved in the Innovation Center. We have a strong portfolio, and we will be very happy to bring some of those projects for a session next year as well, which is the 2024 Innovation Day. So thanks again, everybody, for joining today. I think we can end this session on this note. And once again, I want to thank all the presenters for their excellent presentations.